Welcome back, everybody. In this problem, a plane with initial speed of 95 meters per second touches down on a runway. For the first second, the plane rolls without decelerating. This means that velocity remains constant, whose derivative is 0 during the first second. And then for the next 5 seconds, reverse thrust is applied, decelerating the plane at a rate of 4 meters per second squared, and then eventually the brakes are applied with reverse thrust increasing the rate of deceleration to 8 meters per second squared. First, we want to know how long it takes for the plane to come to a complete rest, and then we would like to know how far does the plane travel before coming to a complete stop. So I'll break the motion into 3 phases. Phase 1, acceleration is 0. Velocity, which is the same as initial velocity, remains at 95 meters per second during the first second. And then phase 2 of motion, acceleration is negative, meaning it is a deceleration of -4. Excuse me. And then for the third phase of motion, acceleration is -8 meters per second squared. Now recall that acceleration is derivative of velocity, therefore velocity is integral of a dt. Since acceleration is 0, velocity is going to be 0 plus c, and since initial velocity is 95, velocity as a function of time during the first second is still 95 meters per second. Then let's continue to phase 2. Then I think it will be helpful if I also draw the acceleration diagram. So for the first second it's 0, then for the next 5 seconds it is -4. Let this line represent -4, and then it goes to -8 for the rest of the motion. So this is the acceleration diagram. A is -4 here and -8 there till it comes to rest. So for the second phase of motion, we can solve for velocity by integrating acceleration, which is -4 with respect to time. So this gives us -4t plus the constant of integration, which can be evaluated. Since velocity at 1 second is 95, if I plug -4 times 1 second, then I can find the constant of integration to be equal to 99. Therefore velocity as a function of time is going to be -4t plus 99. So this is the velocity function for the second phase of motion, which ends at 6 seconds. Then if I plug 6 seconds in this equation, I can know what the velocity is at the time of 6 seconds. So -4 times 6 plus 99 gives us 75 meters per second. This is velocity at 6 seconds, which is going to be used to find the next constant of integration. So for the third phase of motion, velocity as a function of time is integral of acceleration, which is minus 8 dt. This gives us minus 8t plus c. So if I plug c equal to, if I plug velocity equal to 75 at 6 seconds, I can find the constant to be, let's see, 75, and then that is 4,823. Therefore, for the third phase, velocity as a function of time is found to be minus 8t plus 123. So at this point, we have found the velocity function in terms of time for the entire motion. Now we know after some time it is brought to rest. So if I take this equation and let v equal to 0, I can solve it for the time of travel. So let this be equal to 0, and then t, if I divide 123 by 8, I get 15.375 seconds. So this is the time it takes for it to come to a complete stop. Now, we can draw the velocity diagram as a function of time. Observe that for the first phase, it's constant, so it should be drawn with a slope of 0. For the second and third phases, it is a linear function, t to the first power with a negative slope. So let's go to the next page and draw the velocity diagram. And then I can draw v versus t. Let's say this is the vt diagram, v of t versus t. For the first second, it's 95. Let's say this represents 95 for 1 second. And then I want to draw a linear line, linear function, straight line with a slope of -4. So let this be that function. And then for the third phase, it has a negative slope of -8, which is steeper. So I'll draw another straight line like this. So this is the time of 15.35. So here I have 95. Then I have, for this linear function, I have -4t plus 99. And for this third part of it, I have -8t plus 123. Then as far as the second part of the problem is concerned, total distance traveled beyond the initial point when it touches down, we are after x function, position function in terms of time. So let's take one piece at a time. First phase 1. Well, we know velocity is derivative of position, therefore position is integral of dvt. And for the first part, we have a constant velocity of 95, whose integral is 95t plus a constant of integration, which is 0 if we consider the touchdown point as the initial position. Now, if I plug 1 second, xr1 is going to be 95 meters during the first second. Then for phase 2, x as a function of time equals to integral of v dt, but this time v is minus 40 plus 99. So I want to integrate this function, which gives me integral of minus 40 is minus 2t squared plus 99t plus some constant, which can be found if I plug 95 meters for x and 1 second for time t. So 95 equals to minus 2. 1 squared is still 1 plus 99 times 1 is 99 plus c. This can be solved for c to get minus 2. Therefore, position as a function of time will be, let's see, minus 2t squared plus 99t minus 2. So this is the position distance as a function of time for the second part of motion. Then if I plug, observe that right here we have a time of 1 second. At this point we have a time of 6, and recall from part 1 t prime is 15.375 seconds. So if I plug x equal to 6 at x equal to 6 seconds, I have, let's see, minus 2, 6 squared plus 99 times 6 minus 2. This gives me a total distance of 520 meters, which is going to be used to find the constant of integration for the next phase. So let's continue with phase 3. 1, 2, 3. Again, x as a function of time is integral of v dt, but we found v to be minus 8t plus 123 times dt. Integral of this is going to be minus 4t squared plus 123t plus some constant of integration, which can be found if we use the value of 520 in this equation at the time of 6 seconds. So then I have plus 123 times 6 plus c. Solving this equation will give us a, let's see, solving this equation will give us a c equal to minus 74. So taking a calculator and figuring out c, that's what we get. Therefore, x as a function of t for this part of motion is, let's see, minus 4t squared plus 123t minus 74. So that is the last equation for position x. Now the question was, what is the total distance traveled? We have the equation, we have the corresponding time, so I can plug 15.375 in this equation. 15.375 squared plus 123 times 15.735 minus 74. Taking a calculator and doing the numerical calculation, the distance to stop is x equal to 871.6 meters. So that is total distance traveled. Observe that we have three equations for position, therefore we can draw the graph of x versus t. So let this be one axis and let this be time axis. Oops. So t goes there. Suppose I mark this as 1 second and this as 6 and that as 15.375. I want to graph three equations x in terms of t. Observe that the first equation is a linear function, 95t. I box it here to draw attention to it. So for phase 1, I have a linear function with a constant positive slope. Therefore, I should draw this, a linear function with positive slope. For second phase, I have a quadratic function with a negative leading coefficient. Therefore, it should be concave down. For the third part of motion, again, the same thing, quadratic function with a negative leading coefficient. So both of those are going to be concave down. I draw some curve to represent those here. So let this be, okay. Observe that I can also show the corresponding distances at the corresponding points. At x equal to 1, we have 95. At x equal to 6, if I plug 6 in this second equation, for position I have a value of 520 meters, and for the time of 15.375, if I plug it in the third equation, I have 871.6 meters. So these are the three corresponding equations. 95t here. It's not legible, so let's rewrite it again. 95t here. Then I have minus 2t squared plus 99t minus 2 there, and the third equation is for this portion minus 4t squared plus 123t minus 74. So this shows you another example of how the relationship between velocity, position, and acceleration is. Thank you for watching.